There we go. So a couple of things I just wanted to make mention of. I realized that, again, while this is not ideal, I am taking attendance. So I did during normal class, and it's not for a grade. It's merely for me to have a record of your participation. So I wanted to make sure that you understand how that was working. When you log in to Zoom like you are right now, Zoom actually keeps a record of the fact that you logged in, when you logged in, how many minutes you're here. Some of you are having some connectivity issues, I think, because it's like the report would say you're in for 20 minutes, then you're in for 5 minutes, then for 7 minutes. So, I mean, that's fine. At least you're coming back in and logging in and finding it. But if you are here for the 50-minute duration of class, it shows up in a log in a Zoom report that I can run, and I'm going to count you present. If you haven't been able to join for the last 2 days, those lectures are posted. They're MP4 files. They're all around 50 minutes because that's what class will be. And as you learn, we'll run a report for me that tells me who accesses those videos. So if you aren't here with us live, I'll go there and see if you watched it recorded, and at the end of the week, I'll take attendance. Okay, you're welcome to go back and look at them. But, and again, it's not for you, it's for me, but it'll sort of be for you. You know, like there's a couple of pre-calc students that I have that we've met 3 days now, and they've not attended one session, and they've not accessed any of the lectures online. So to me, it's like they're absent. So I'm going to reach out, see what's going on, see if they're having issues getting something where they can participate, because that's a problem. You know, at the end of the semester, you get a grade, and what you learn here is what you'll have as your background going forward. So I don't want to shortchange anyone, but the expectation is, you know, you're here. I lectured just like I would in Walker Hall, but now I'm in the kitchen today, with some dryer going on in the background and children running around somewhere. But before we continue with chapter 4, does anybody have questions on anything? Connectivity, access, sapling? No. I did add, so I think I emailed out about this because we're just going to have a whole lot of email now. That's just the thing. In As You Learn, I did put a block of the online tutoring information that we have now. So what we, hold on, let me get this to where it'll just be, there we go. And Hannah's here. So we have the online 8 to 11 p.m. 3 nights a week. That is, I mean, I got an email last night from the guy that runs it in our statistics department. It's going 8 to 11 p.m. You click on this, whatever this website is, and there's a link for Tuesday, a link for Wednesday, a link for Thursday. Just make sure you click on the right one. And it's 3 hours of later at night tutoring. The math lab that used to be in Walker 103A is still functioning, but in a Zoom session like this, I mean, it's just the way of the world right now, unfortunately, and we're going to deal with it. But it's a Zoom session. You click on this link. It's 4 to 7 p.m. What is that? 1, 2, 3, 5 days a week. So it's still there if you want to use it. And it's not perfect, like they said. They said it won't be perfect, and they're working out the kinks. But it's like this, I would like to imagine, or it should be, because I think it would be handy. But that information is there for whoever wants to access it. But I mean, you are most welcome to shoot me an email and say, you know, hey, I'm still not understanding this. Can we maybe get together sometime later? I mean, other than hanging outside or, you know, just piddly work pretty much at this point, helping the boys with their homework. I mean, I can get online pretty quickly if you just request it within, you know, like an hour's notice. But you just let me know. Dinner time's pretty quiet, and when they do baths and lay down for bed, it's pretty quiet. So I'm happy to hop back on here, pull up sapling, write something out on my iPad, whatever would help you understand it a little farther. You let me know, or you can use the math lab. Totally up to you, but there's lots of resources out there. The effort will be in your court once I've presented the material. So with what we started yesterday, can share some iPad if it would like to work today. If it would like to work today. You are connected. Come on, connect. It had this issue yesterday evening. It's not going to connect, is it? Let's try one more time. We started, see, section 4.2 was the absolute and the local extrema and finding critical numbers. And then we started section 4.3, which really, even though it's called the mean value theorem, again, it's a theorem in calculus. But if you want to read about it, you can. But we're jumping to this concept of an increasing, decreasing function test. I think I have to check on the first derivative test as to whether or not those might be two different things, because there's a first derivative test and there's a second derivative test. Hey, buddy. And the increasing and decreasing function test is basically a test that uses calculus, even though I know you can graph it and see, but it's a test that uses calculus to show the work to figure out intervals where the function increases and decreases. We did this visually before, maybe in one of the first chapters, but now we're going to do it using calculus, and that's what the directive will say. That's what your quizzes and tests will say. It'll say using calculus, show where the function increases and decreases. So the notion here is wherever the derivative is positive, then that's where the function increases. Wherever the derivative is negative, that's where the function decreases, okay? And in order to find those intervals where it increases and decreases and where it's positive and negative, we have to consider the critical numbers. So for the most part, it'll be take the derivative, set it equal to 0. Polynomials are pretty easy. Rational functions we have to watch out for. Square root function, the domain will become part of what you have to consider for some of these. Anytime you have asymptotes, those have to be considered. Anytime you have places where there are sharp corners or cusps, like absolute value functions have corners where, or cusps where it may not be differentiable, so that's considered a critical number. So all those things you have to consider whenever you try to come up with these critical numbers. And I looked, the 4-3 homework, it's chunked with 4-3, 4-4, and 4-6, I think. But I was clicking through some of the 4-3 questions, and basically those ask you for critical numbers, or they ask you where a function increases and decreases. So before we get into some of these questions, I wanted to real quickly, this is really for some of the pre-calc students I know that I had. If you had an inequality notation where a number was in between 1 and 4, the pre-calculus book that App State uses did this inequality notation. If you chose to instead do that with interval notation, which I tried to teach and talk about for the students that I did have, but it wasn't recognized by the textbook. If you were looking in between something 1 and 4 and you included them, you used brackets, put the numbers with a comma, and that was your interval. If you didn't include them, you would use parentheses. If you looked for a number that was greater than 3, the interval notation would have went from 3 to infinity. If you went numbers lower than -1, you had to put negative infinity to -1 in that order. Negative infinity is always on the left. Positive infinity is always on the right. And that's really the gist of like interval notation. And interval notation is what we are going to use to report where things increase and decrease in sapling. So if you're not as familiar with interval notation, get familiar with it, because that's how you have to input your answers. Another thing that shows up for answering is like, you know, if you had a number line and here's 0 and here's 4, and you went everything above 4 and everything below 0, as an inequality, it was 2 inequalities. It was all x's under 0 and all x's above 4. If you write that in interval notation, there's 2 separate intervals, and the software for this textbook, instead of writing the word and is going to get replaced with that union. And I think in Sapling there's a tool for it that you can click. So it would be like negative infinity to 0, union 4 to infinity. So the union, again, this is a symbol for union. It's combining 2 sets together, union of sets, not an intersection. So these show up in the way that you have to answer questions for your homework. So I just thought I would mention that before we started writing interval notation, and some of you were confused as to what we may be doing. Okay, so put Brian in the course, and then we'll start. So I have a few examples that should model a lot of the ones that are in your homework. Some polynomials, some power functions, some, I think I don't know if I have a quotient rule or not, product rule, but any of those rules that we've done before are game for questions in this entire chapter. The trig functions, the inverse, the natural log, the square root written as a power. So we're going to start with, I think we started this one yesterday, but I'm going to do it again and just take it the step further to figure out where it increases and decreases, do it in its entirety. So here you have a function, and the question will be to find intervals where the function increases and where it decreases. So that will be the directive here. And you'll have answer blocks where it says increasing, answer block where you input decreasing to make sure you don't flip those. It's real easy to flip those because they're not always in the same order. But in order to figure out where it increases and decreases. So here's the reality of the situation I know that you're in at home. You could graph this thing and look where it increases, where it decreases, because it's cubic, it's going to come up, come down, come back up. And you could probably pick the points and eyeball it. But you are going to be required, if you would like a decent grade on your quiz or your test, you are going to be required to show the use of calculus in order to identify where these increase and decrease. Okay, so the way that we do that is, first we're going to find the derivative and get our critical numbers, because our critical numbers are in fact critical to tell us where it may change from increase to decrease or decrease to increase. So critical numbers are where we find that the derivative equals 0 or where it's undefined. And in this case, I don't think we're going to have any undefined because it's polynomial. Anytime you have, like I said, rational functions where you divide by 0, or absolute value functions, any piecewise functions, anything that create something that's not differentiable would have to be considered a critical number too. But for now, we're going to start with this function. It's a nice polynomial. The derivative is 6x squared minus 18x plus 12. And if we want to see where that equals 0, I mean, it's quadratic. You factor it. If you want to do the quadratic formula, you can. That's up to you, but this one should factor. If I pull a 6 out, it's 6x squared minus 3x plus 4. And then if I factor further, I get x. Did I write that down wrong? That's not a, that's a 2. I was like, wait a minute. Just kidding. That would be 24. I'm like, that's not going to give me 4. That's a 2. Minus 2 minus 3, or minus 2 minus 1. Long morning. So if you can get it factored, it'll be set each factor equal to 0. Nothing will come of the 6, but x minus 2 would give us a critical number of 2. X minus 1 would give a critical number of 1. And those are our critical numbers. Okay, so if we have these, let's make sure, I feel like I missed something here, but in order to take these and sort of figure out 6 times 3, I guess I just wrote a different question down because it just looks weird. No, we're good. Okay, so from here, you take your critical numbers. There's 2 and 1, so these are going to be important for this question. And we're going to create, some of you, if you've had this before and had instructors that did this differently, I need to consider the number 1 and the number 2 and everything around it. So numerically on a number line, if I look at 1, I got to look below it, I got to look in between 1 and 2, and I got to look above 2. So I was always taught to make this little sign chart. Some of you just make it like a number line. But if I consider, so this is sort of like, now we're testing for where it's increasing and decreasing, and we're using these critical numbers. So give yourself some space. My critical numbers are 1 and 2. So I need to order them in the right order. So I'm going to put 1, leave a space, put 2, and leave a space, and then look everywhere around them. So here I can choose any number that's less than 1. Anything that you would like to pick at all. I'm going to go with 0 because 0 is easy to work with. Okay. In here, you can pick any number that's between 1 and 2, like 1.5. You don't have to get fancy or creative, but if you want to, square root of 3, go with that. Doesn't matter. But any number that lives within that interval is perfect to test for this. Okay. Then the last one needs to be any number that's above 2, like 3 or 4 or 5 or 10. Doesn't matter. Then the next row, or the next thing to consider, is going to be the sign of f prime. And it's either going to be positive or negative. That's what I mean by the sign. I don't really care what it is. I'm not asking you to evaluate the function or the derivative at that number, because that would be a slope for a tangent line. I'm simply asking you, is it going to be positive or is it going to be negative? Because we talked about this before. Anywhere the derivative is positive, the function is increasing. Anywhere the derivative is negative, the function is decreasing. 1 and 2, you can either like scratch them out or write that it's a critical number, something to indicate that we're not really using it for here. I think what I usually do is indicate the fact that it's a critical number, and I'm not really interested in it because it made it 0. If I plug it in, it's going to be 0. So if I take 0, like the number 0, and I take it and I plug, again, we're going into derivative. So the easiest derivative to plug it into is probably going to be the factored form. If you plug a 0 in for all of the x's, or even if you plug a 0 into the original derivative, again, I don't really care that the answer is 12. What I care about is the fact if I plug 0 or anything less than 1 into that derivative, then my answer is going to be positive. That's the interest here, is that it's going to be positive. Okay? And it'll be the same thing for the next one. Try to get this in here. If I plug in this 1.5, again, you could have done 1.1, 1.2, 1.01. It doesn't really matter. If I take and I plug in 1.5, just like I did the other one, and if you need to do some scrap work over here on the side, you can, 6, and then 1.5 minus 2, and 1.5 minus, again, the value is not what's important. I don't think you can see that. There we go. The value is not what's important. The sign is important. So 6 is positive, 1.5 take away 2 is negative, 1.5. So this is going to be negative. Again, if you want to plug it in, but what you're recording is the sign of it, positive or negative. If you plug in 3 here, if you want to take this, or any number bigger than 2, 6, 3 minus 2, 3 minus 1. Again, I don't care what the number is. I care about whether it's positive or negative. And that product, if you plug in 3 or anything larger than 2, you're going to get a product that's going to be positive again. Okay? So if you have places where the derivative is positive, then the original function, that is where it's increasing. If you have values where the derivative is negative, that is where it's decreasing. And then when it's positive again, it's increasing. And it's cubic. It should have increased, decreased. That's what it should have done. Okay? But now we can report intervals. So again, I like to think about this like a number line. where this was a critical value, this was a critical value, and here it's increasing. Between 1 and 2, it's decreasing, and above 2, it's increasing. Some of you were taught to draw a number line like that when you did it before. Whatever works for you, but you're going to have to make some sort of chart work to show that you're looking at whether the sign is positive or negative. Okay, so when you report them as intervals, if any number less than 1 creates a positive derivative in an increasing function, then we say that this is increasing from negative infinity to 1. And we also had, anytime we went bigger than 2, we also had an increasing function. So we'll say, oh, that zoomed out really weird, that this function increases -1 or negative infinity to 1 and 2 to infinity. Like, you have to do both of those together in one answer space. If we talk about where it's decreasing, any number that we would have chosen between 1 and 2 would have created a negative derivative and thus creating a decreasing part of the function. So it's decreasing in between 1 and 2. Okay. So I wanted to note here that in pre-calculus, like when you get to that 1 and then it switches to decreasing and then it increases again, at that peak, it's not really increasing or decreasing. So you're not supposed to include those endpoints, but just so you know, Sapling will take it if you use a bracket instead of a parenthesis. I don't know why, I wish it didn't, but if you have issues with brackets versus parentheses, let me know. Okay, but it should not include it whenever you look at where it increases and decreases. And we can take, like, if you want some visual justification, 2x cubed minus 9x squared plus 12x plus 5. I mean, maybe it would help if you had that. You know, here's a peak at 110 and a peak at 29. So it's increasing up to 1, and then 1 to 2 it's decreasing, and then it's increasing. I mean, I know that you could pull a calculator and look at that, and that's using a calculator. If we use the values of the derivative, that's considered using calculus to show it. And then you can graph it if you want to check your work. Okay. I'll pause for questions. If anybody has any that you'd like to ask or chat or comment. You're good? Everybody's good? You can pull up your pictures. Okay. Somebody keeps kicking out. Okay. So the difficulty in this, I don't think will be the chart part, or maybe it will, I'm not really sure. The degree of difficulty in that function to get its derivative and critical points is where some of you are going to have some questions. Okay, so you'll just have to try to figure out the rules that we've done in the previous chapter, revisit those if you need to. Maybe that's what you need to do tutoring at Math Lab. I don't really know. But here is, what is that? Oh, we did that already. Here's another one. We'll do the same thing. And like I said, sometimes it asks you for just the critical numbers, and sometimes it asks you for where it increases and decreases, and sometimes it's both. I mean, I would ask you for both. But for this one, same thing. Find the intervals where it increases and decreases. Okay. You'll have to let me know if you chat. Okay. So for this one, what will we use to get the derivative? Anybody that would like to shout it out or chat it out? No takers? Jeremy says power function, power rule. I mean, just power, or are we going to have to do some other stuff with it? Go to this chat. Chain, I see 3 different chains. So yeah, we'll power it to begin with. And then once we bring the power down, keep it, subtract 1, we'll have to chain the inside. Okay, so that's where we'll start. And once you have the derivative, then it'll be your job to figure out the critical numbers. And this one, I mean, watch out for undefined as well as 0. So if we do the derivative, yeah, it'll start with power rule, and then we'll have to chain the inside. Okay, I'm trying to keep up if you guys talked, but now you're using chat to literally chat with each other socially. So if we can, let's try to reserve chat for questions. You're welcome to chat later, but if this chat thing pops up, I got to make sure nobody has a question. So the derivative, if we bring power rule down and we subtract 1 from 2/3, that's 2/3 minus 1, so that's negative 1/3. And then we'll do the derivative and chain the inside, and that's 2x. Okay, so here is where I tried to stress it in chapter 3, but now you have to understand how to simplify these if you want to pull the critical numbers correctly. Okay, so I have a quantity. Oh, that's not you. Where did you go? There you go. I have a quantity here with a negative exponent, so I'm going to rewrite it in the denominator and make it a positive exponent. So I've got a 2 and a 3 with an x squared minus 1 to a positive 1/3. And then this 2x that got multiplied, it's going to join this 2 as a product in the numerator. And really, it's going to be a 4x. So if I do 2 with 2x, my numerator is now 4x. So there is your cleaned up version of the function. And if you wanted to, just so you could, I don't know, numerically understand things, x squared minus 1 to the 1/3 is the same as cube root. It's up to you whichever way you want to look at it. But from this, we have to find the critical numbers. So anytime you have a rational function, you have to consider both areas, both the numerator and the denominator. So anything that would make the top 0 is going to be a critical number, and anything that makes the bottom 0 is going to make the derivative undefined, and any of that combination would be a critical number. Okay, so the only critical number we get from the top is 0. And how about critical numbers from the bottom? Will anything make the denominator 0? Let me see if you want to chat that one out. If I can find somewhere to set this chat box. I know, Fernando, if you guys just talked. Just kidding. No takers? Critical numbers from the bottom? Oh, we got a chatter. I got a 1. Anything else?
Where did the what happened to the numerator?
I barely hear anything. Whoever that is, I can't hear your volume.
What happened to the numerator?
So what happened? The 4x?
Yeah.
So from that quantity, the only thing that's going to make 4x 0 is the number 0. So nothing happened to it. We just pulled the critical number of 0 from it. Does that answer your question?
Yeah.
Okay. I didn't know if you wanted to know where this 2 went. It combined with the 2. I guess I could have highlighted that and said it joined forces. So yeah, I saw the chats, a couple of you roll in. If you look at the denominator, that x squared minus 1, anything that would make that quantity 0 is going to make it undefined. So not only is 1 a problem, but yeah, well, it would be square root plus or minus. So you have to consider both the positive and the negative of 1. So like if you set that equal to 0, when you square rooted it, you'd have to consider both positive and negative 1. Because if you plug in 1 and square it and subtract 1, you get 0. If you plug in negative 1 and square it, subtract 1, you still get 0. So both of those are going to be considered things that make the derivative undefined. They're fine in the original function. Well, maybe not 1 in the original function, but as far as being a critical number, it's what makes the derivative 0 or undefined. So those are the numbers that we use when we try to figure out where it increases and decreases. So there's 3 of them. So you got to look, I mean, if you need to imagine some grade school number line going on, this is what we're looking at. We're looking at everything, any value below -1, anything in between -1 and 0, 0 to 1, and everything above 1. Those are going to be the intervals that get pulled from this. So You can do it in a number line. I mean, like I said, I was always taught to make this chart, and it helps. But here's -1, here's 0, here's 1. And then again, you have to look everywhere above and between, below, however you'd like to look at this. And then we're going to consider the sign of the derivative. I'm not interested in the value of the derivative, but just whether it's positive or negative. And then that's going to drive our function being increasing or decreasing. So 1 is negative. This is critical, critical, critical. Okay. So here we'll go any number that's below -1. Any number that would live here on the number, that's terrible. Here on a number line. So -2, -5, whatever you'd like to pick, it's up to you. And here we'll go any number in between. So in between -1 and 0, any number in between 0 and 1, and then over here will be any number that's above 1. So use your imagination, but you don't have to get, I mean, don't get crazy. Or get crazy, I don't really care. Just pick a number that numerically lives in that interval that you've split up, okay? So the derivative, again, is you pick either one of these, it doesn't really matter, but what we're interested in is the sign of it. And if you need to set it up in an equation and try to guess it, you can, that's totally left up to you. But if you took -2 and plugged it in for those input values, it's negative on the top and it's positive on the bottom. So, I mean, if you need to write that, please write it. Because again, we're doing like 4 times -2 and 3 times -2 squared minus 1 with a 1/3. I mean, the bottom is going to be positive because you're squaring a negative, you're subtracting 1, it's still positive. You're going to cube root it, it's still positive. You're going to times it by 3, it's still positive. But the top 4 times -2 or -5 or whatever you decided to plug in, you have a negative over a positive, and that quotient is negative. That's what you have to be able to do with these derivative signs. Is again, it's not really the what it is, but if you want to calculate what it is, that's fine, but that's not what you're recording. If you plug in -1/2, again, if you need to scratch it out somewhere, or if you need to type it into the calculator, you can, but you've got 4 times a negative number up top and 3 times a -1/2 squared on the bottom. So the top is negative. If you square a half, it's a 1/4. And if you subtract 1, it's negative. And if you cube root a negative, it's still negative. So this one produces a negative over a negative. So this derivative is positive. And again, if you just want to plug it in and get the number, go for it. But the number is not what's important. It's positive or negative aspect. Okay. If you plug in 1/2, it's the same thing. You're going to get a positive up top. And if you plug in 1/2, I think you get a negative on the bottom because you're squaring a half and taking away 1, it's negative. So this quotient is negative. And if you plug in 2, you get a positive up top, positive on the bottom, and that ratio is positive. Again, if you want to put it in a y equals and go to a chart, that's completely left up to you. But you have to be able to understand if the derivative is negative or positive there. So then when we go to talk about the function, wherever the derivative was negative, that's where the function is decreasing. Wherever it's positive, that's where it's increasing. And then it flips to decreasing, and then it's increasing on the end. And then you'll take those and you'll pull them as intervals. And if the number line part helps you, then draw it again. It's okay. Because we found out, again, if you want to draw the number line down here, we can. Here was -1, here was 0, here was 1. The only numbers that should ever appear in your intervals of increase or decrease are critical numbers, not the numbers that we plugged in. It's the critical numbers that show up because they're critical. That's where it switches from one to the other. Okay, so it's decreasing, then it switches to increasing, then it switches again to decreasing, and then back to increasing on to infinity. So intervals where it increases, are -1 to 0 and 1 to infinity. And intervals where it decreases are -infinity to -1 and 0 to 1. That's what you would answer for those. Thoughts, concerns, questions? Because this part of it isn't going to change. This is called the increase and decrease test for derivatives with functions. You take the derivative, you find its critical values, you test around them, and that will show you where the function is increasing and decreasing. And if you want to graph this, we can. I think it does one of those. I think it does one of these. It comes down and it comes down, it comes up. So it decreases, increases, decreases, increases. So you're welcome to look at that if you want. Oh, Granny, no. Granny's calling. She's 89. She needs people. Any questions? Now would be the time to ask. I heard a no. I see a chat. The critical numbers. Yes. So the critical numbers, again, once you find the derivative, you have to figure out where it's 0 or undefined. And in this case, because the function was a rational function, we had to not only consider the numerator, but also the denominator. Okay. Okay. So again, depending on the question, this can be harder, this can be easy. I mean, I've got, I have another one, and I have an absolute value, and I don't know that one is harder than the other, and it's, what, 140? We can do this one, and we can do more tomorrow. You can, I mean, you should be finishing up with the 3-5 and the linear approximation stuff, I think today, or I think that at least the guided learning today, homework Friday. So you can move on with this homework and ask questions if you have it. And I can do I might do the absolute value example tomorrow because I know there's one on your homework. But like for this problem, when I first saw it, I was like, oh, God, product rule. But I don't think you have to use product rule. You can use product rule. But because it's a power function and this is not anything weird, it's just a polynomial, if you distribute, oh, that's a highlighter still. Then you get the original function, what is that? Add exponents, right? If you multiply, you add, so 1/3 plus 1/2. What is that? Oh, why is my brain not working? 7/3? Yeah, is that right? And then 7x to the 1/3. And then this is a really nice power rule. I'm about to put you on camera because you're high maintenance, kid. So, I mean, once you get it into terms like this, if you want to use quotient rule, you can, but you don't have to because I think it gets a little messy if you do. But we can just use power rule. So if we do the derivative, Carter, if you can't be quiet, leave. Power rule. So 7/3 x, bring down the 7/3, leave the x, subtract 1. So does that leave what, 4/3? And then you have the 7, you bring down the 1/3 and multiply it, right? And then subtract 1. So you get -2/3. This looks really weird, but it's, so far it's right. Okay, so what we have is 7/3 x to the 4/3 minus 7/3 x to the -2/3. Yes, be quiet. Yes, this is the 6-year-old. I told him I'm about to put it on him. He's trying to write his numbers from 1 to 150, and it's taken him 3 days because he thinks it's boring. And he's 6. He's not wrong. So here's where some of the tools that we used before in the chapter, the previous chapter, you're like, I'll trade you. Some of the tools that we used in previous chapters are going to become important because if you want to know where this is 0 or undefined, you're going to have to make a single term, factor, combine like terms. You're going to have to do something to make this a single term. Like you can't just look at that and be like, oh, I don't know. What would make that 0? 0? Who knows? Because it's not just 0. So you're gonna have to sort of like do a little bit of math and try to combine. And this is where I think a lot of you are gonna find your weakness to be. Trying to see, I worked this one out earlier, but I wanted to work it out with you so you could maybe revisit some of the skills. I'm going to put this negative exponent in the denominator. So 3x to the 2/3. And now I need to make a common denominator. So what the goal here is to get to be a single fraction. Because if you can get it to be a single fraction, like a rational function, then you can sort of look at what makes the top 0, what makes the bottom 0. So common denominator, they both have this 3, but I'm going to give an x to the 2/3 both to the numerator and to the denominator. Okay. So if I do that, oh my gosh, seriously. I need to turn my phone off, right? Because we're having class. So my denominator is 3x to the 2/3. I didn't really do anything to the right fraction, but what happens up here in this top piece? Because all of these are in the numerator. I've got a 7. And if I do x to the 4/3 times x to the 2/3, that's going to add and be x to the 6/3, which is x squared. Okay. And then if I subtract across the top, I get 7x squared minus 7 over 3x to the 2/3. If you factor 7 out of the top, see, I promise I wasn't trying to make you do extra work in chapter 3. I was prepping you for this, because unless you can algebraically combine this and get it to be a single fraction completely simplified, this is what I mean by doing completely simplified. Now, in this form, I'm pretty confident that most of you could tell me what would make the top 0 and what would make the bottom undefined. Pretty confident that most of you could tell me that. Critical numbers from the top, plus and minus 1, right? Because it's x squared minus 1, both positive and negative 1 would make that 0. Critical numbers from the bottom are going to be 0, because you can't divide by 0. So you have 3 critical numbers here, and the box will look a lot like the question that we just did. And we are running out of time. Do you have questions yet? Because this, all of this is pre-calculus and high school algebra combining like terms. And we've worked on it. Some of you are really weak at it. If I could fix it, I would be happy to. But this is what some of you need to practice and possibly get some tutoring on, is how to take these terms that you need to get into common denominator with a single fraction and practice it. I mean, there's tons of examples out there. There's probably videos galore till we break the internet that you can pull up and look at. If you want to do some office hours with me, I'm happy to come up with questions to help you practice this. But otherwise, you know, it's not like you can exactly look at this and come up with 0, 1, and -1 for your critical numbers. And if you did, I would be like, how'd you get that? Did you use your calculator? Okay, but I need you to use calculus, not calculator. Okay, so once you come up with critical numbers, I mean, you're doing the chart, and I might just switch it back to this page here. And I'll post these too so you have them, because like I said, I think we're running out of time. But you don't really need this mess. Well, I can't really erase it. Don't pay attention to this mess yet. We'll do this in the next section. And that all went away. But it's still critical numbers of -1, 0, and 1. It's okay. It's water. It'll dry. I promise. Critical numbers of -1, 0, and 1. So test below, in between, above, and then you'll figure out where your functions increase and decrease. Anybody have questions or concerns or comments or anything? Anybody? You're good? I can't see your faces. If I come over here, maybe I can see your faces. Okay. So much energy. You're good? Okay, I mean, it's just like in class. If you guys are sitting here and you're totally confused and you don't say anything, I literally can't see it now because most of you aren't sharing your screen. So please speak up if you have questions. Please reach out and email or attend the math lab if you like those people better. Whatever will help you, please try to figure out a method that will help you with this because, I mean, I'm doing what I can on my end, and I don't know that you're, oh yeah, algebra for sure. I mean, I'm telling you, calculus is not hard. Algebra is the hardest part of calculus and pre-calculus. So it's just the practicing of the combining like terms, knowing when to, especially if you can't just, you're not dumb. You guys, each of you got into Appalachian State. You're not dumb. I promise you. You may be weak at algebra, but you're not dumb. I promise. So anyways, I'll post these. I actually ended up posting some extra examples for linear approximations yesterday after it dawned on me that that I didn't post many. I thought I had some posted, but now there's some extra. Yeah, please. Yes, Paige, I encourage you to FaceTime or, I mean, you have access to Zoom, but I don't know if you can do Zoom accounts or you can do Skype or there's lots of something. Microsoft has something. I don't know what it is. My brother-in-law uses it. Anything that would help you guys understand how to do this. And if there's a group of you and you're lost and you're completely lost and you're like, Ms. Puckett, can you please meet with us at like 7 o'clock because we are so lost. I'm happy to do that. Okay. But you have to be willing to participate and reach out and not be afraid to talk or ask or try it because I'm going to have to give everybody a grade in May. And whether it's online or not, like I said, I have some colleagues who have pre-recorded lectures, shove them online and say, hey, go watch this. And that is not the way that I want to deliver this course. It's not the way, it's not the way that I wanted to deliver it. It's not my choice. So here I am in my kitchen with my iPad, giving you notes like I would in classroom. So the extra level of participation will be up to you, and I'm happy to help you however I can. You can make videos. If you need some extra help, you can Google videos. There's hundreds of things out there that you can look at. But we'll do more. Like I have an absolute value example that I could show you because there's one on the homework. And then where this goes into chapter or section 4.4 is the acknowledgement that if you have a function that decreases, then it increases, there's a minimum there. And if you have a function that increases and then it decreases, there's sometimes, depending on if there's an asymptote, there could be a maximum there. So we're also going to use this increase and decreasing test to come up with where the extrema, the minimums and the maximums are, the local ones, because if it's a polynomial and it goes forever. So we're going to use them to find local extrema in section 4.4. And I think concave up and concave down shows up there too. And we'll use second derivative for that. So your ability to take the derivative and simplify it is crucial for this chapter, which is why we spent so much time in chapter 3. Okay, so I still got to get your tests scanned. If you're like hardcore dying to know and look at your tests, email me and I'll make sure I'll do that one first and email it to you. But check your email for any updates, any changes, which I don't anticipate there being changes. I'm pretty sure you guys have access to each other in As You Learn. I feel like maybe you can get each other's. I mean, you're more than welcome to share emails on chat. But I feel like you can contact each other in As You Learn. I'm pretty sure because I think I've had some students say that they have before. So feel free to make whatever group you like in whatever means possible to do as much social online studying as you can. And please reach out to me if you have any questions. Okay. But otherwise, I'm good for the day. I'm gonna stop recording, let it upload here in the next 30 minutes. But you please let me know if you have questions, okay? Good luck. Stay safe. Wash your hands. Okay. I'll see you tomorrow.